2-minute warning before questions start, okay?
Thanks. So first, I want to mention that Wang, who is an undergraduate student working with me, did the most of the real work, but I gave the presentation. Um, so I guess this is the plasma physics view of the art of the moon, and apparently the lunar surface is charged by solar wind, electrons, ions, secondary electrons, as well as photoelectrons due to the UV radiation. So the dust particles on the regolith of this surface will also be charged and may move and even get lofted due to electrostatic forces. So here are some in-situ observations that may link to this electrostatic dust transport scenarios. So this is lunar horizon glow, and this is the fine deposition of dust particles in the bottom of the crater on asteroid Eros. And here are the spokes, is dark lens in the Saturn's rings. And very recently, Rosetta has collected this very fluffy dust particles coming off the comet. So in order to understand this electrostatic dust transport, we have done several laboratory experiments in the past. So on the left is one of them. So we have a dust particle sitting on the surface and also next to the higher terrain. When plasma is turned on, you see the particles spread out and also accumulate on top of the higher terrain, which indicate both vertical and horizontal motions. So Flanagan and Gorey also detect the lofting dust from the light scattering. So when dust particles hopping off this glass ball and hit the laser above, so they will create light scattering as shown here. So we did see dust moving, hopping in the laboratory. So then the fundamental question is, how does this work? What are the exact charging mechanisms? So here I will show some quick calculations with current charge models. First, it's called a shared charge model. It's basically assume each particle takes same amount of charge. And we can calculate the charge Q from the Gauss law with the electric field in the plasma sheath. Then you get Fe is Q times E. And also there's the particle-particle repulsive, or say Coulomb force, that's Fc, and the gravitational force is Fg. So we did two cases. First is for the experiment I just showed in the previous slide. So the total electrostatic force, Fe plus Fc, is 2 orders of magnitude smaller than gravity alone. For the lunar case, it's even worse. It's 7 orders smaller. So here I didn't even consider cohesion force yet. And Sheridan and Hayes derived this equation with the charge fluctuation theory, which is based on the nature of discrete electron ion fluxes to the surface. And putting our parameters into this equation, we do see some enhancement on temporal charge, but not high enough. So the conclusion for now is the charge induced by plasma is way too small for dust particles to be lifted off the surface. So here come our new dust experiments. So I have Mars simulants filling in a crater 2 centimeters in diameter, about a millimeter deep. So the purpose of viewing the crater is for trapping dust particles from spreading out. So that way we can be more focused on dust hopping and lofting studies. So this is the movie. When I started the movie, there was a lot of hopping trajectories, and we highlighted them in green. I don't know why it's stuck there, but it's supposed to be very smooth. You see a lot of hopping trajectories. So the original trajectories are too thin to see, so we highlighted them in green for you to see them. They're pretty active. So this trajectory allowed us to do this study in micro scale, which is we can get a lot of details about that hopping. So this is one of The frames, you see here a lot of trajectories. If you don't see them, here they are. And then we can measure the height, and you can calculate the vertical launch speed. And here are the stats of these trajectories for a period of 1 second. So we counted 244 trajectories. The average height is about 1.5 millimeters. And the vertical launch speed is about from 10 to 30 centimeters per second. So now we can analyze the size of hopping dust particles. So this is cropped image, and after we filtering out this bulk surface and blurred images, and we got this. These are sharp images, so we counted pixels. And then we got a size distribution of hopping dust particles. This is for size from 50 to 60 microns. You see the distribution is very broad. Two red lines bounded single-sized particles. On the left, the smaller sized particles. That's residues on the bigger single particles. And also, you see a lot of clumps due to the cohesion between the particles. As the size comes down, you see more clumps but less residues. When size is smaller than 25 microns, you see basically all the clumps hopping. So the cohesive force is really strong when between smaller particles. So now we're back to the fundamental question I asked for myself in the previous slide. So what are the exact charging mechanisms? So on the left, I have this cartoon shows primary electrons coming down with energy 140 eV, and will create secondary electrons from the surface. And we did a horizontal potential scan. So on the right, it shows that the secondary electrons make the potential on the solid surface much more positive than surface potential calculated without secondary emission. And here, the potential on the dust surface stays more negative than the potential on the solid surface, which indicates smaller secondary emission. So what happens is that there are many microcavities formed by neighbor dust particles. So emitted secondary electrons will be absorbed inside these cavities. They can't get out. That makes the secondary emission from dust surface much smaller than from solid surface. And this is the game changer, I think. So with this drawing, I can show more detail about macro cavity idea. It's 5 circles represent 5 dust particles. So in the middle, that's a macro cavity. And the top 3 particles are exposed plasma. So they will be charged by whatever the plasma particle flux is. In our case here, it's slightly negative. And between these 2 particles, there's a little gap. So the plasma can't get in as a bulk. But the individual particles, for example, is primary electrons carrying higher energy, and ions coming into the cavity hit the surface here and create secondaries. And these secondary electrons will be collected by the neighbor particles. This patch in light blue. So this light blue patch basically only collects secondary electrons. There's no ions. So what happens, the charge will keep building up more negative, until it can stop the high energy tail secondary electrons, which we assume is the Maxwellian distribution. So we expect there's a much higher negative charge inside the cavity. So to test this model, we did a first attempt with experiments. So I have 2 electrodes sitting on top of each other and insulated in between. We put the electrodes in the sheaths right above the plate. And when you turn on the plasma. So here you see the drawing of all the particle fluxes. So the top electrode basically see all the plasma fluxes. However, the bottom electrodes basically only see the secondary electrons. and some thermal electrons. So they collect different fluxes. It's supposed to charge different. And here it is. This is our measurements uh, for the potential on both electrodes and in vacuum and in plasma. It shows the top electrode always charged much more positive than the bottom electrode. And in the vacuum condition, the bottom electrode can be as negative as minus 22 volts. So if you put this voltage for the 60 micron dust particles, you get the charge due to the secondary electron. It's much, much larger than the plasma charge. And here, and the Coulomb force is much, much larger than the sheath electric field force. And also now, it's larger than the gravity. So we have a chance to lift dust particles. And I convert electrostatic potential energy to kinetic energy of the particles. You get a launch speed about 10 centimeters per second, which is this dashed line in this plot. So a short summary is that the secondary electron charge on the patch inside the macrocavity is huge. And the Coulomb force, the portion between particles, is dominant electricity force to lift dust off. Okay. And so now it seems like we have a chance to overcome the gravity, sure. But we didn't see like a plume like hopping, like crazy. So I think the cohesive force is now the bad guy. So we need to do more study on that. So in the end, I don't want to read all of those lines, but give you some keywords. So we proposed patch charge model, secondary or photoelectron charge inside microcavities bounded by neighbor particles. And the repulsive force can be the dominant force to lift dust. And also, the big goal for sure is to apply our lab findings to explain what happens on airless body surfaces. And I think that's it. I can take questions.
How you doing? Hey, great talk. Very interesting.
Just a reminder,
So,
introduce yourself.
Bill Farrell, NASA Goddard. This mic is way too high, by the way. I'm going to point to Jasper Helkes here. You know, when he did work on Lunar Prospector on the night side, he was finding, didn't you find that secondary electron values coming off the night side of the Lunar Prospector were anomalously lower than you had would expect by theory? Could something like this explain that?
That is what we found with LP data, or at least that's one interpretation of the observations we had. I have to think about whether that would play a role here.
Okay. All right. Good.
Yeah, so yeah.
Doug Curry, University of Maryland. Any projections on what would happen on airless bodies like the moon?
Yes, I think that's our big goal. And so here I can't give too many comments because we have to first confirm our theories and models with lab experiments. But I can tell you that the theoretical possibility for dust particles to be lifted off on those surfaces, even on day side, for the electrons can be also powerful. I think this possibility becomes larger than, because like the previous slide showed, with old charge model, there's no way